In this video, I'm planning on going over the equations that you need to solve the least squares approximate solution in linear regression. And I'm going to specifically be talking about linear regression in the context of machine learning. In the context of machine learning, basically we're trying to predict an unknown quantity based on a linear model that we learned from past observations. So the first thing that we need is to define our linear model. So our linear model is going to look basically like something like this. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot dot dot, and then however many x terms we have, so plus beta k xk. And so in this model, the y is our dependent variable. That's what we're trying to predict. So if we're looking at house values, what we're trying to predict is the value of the house. And then x is going to put x. These are called our features, and these are our independent variables. So these are things that we would use to predict what y is. So for predicting house values, these could be things like the number of bedrooms, number of bathrooms, square footage, things like that. And beta, so the betas are the model parameters. This is called the bias term. Say we only have one feature. So let's say that y is equal to beta naught plus beta 1 x. So then this should look familiar. So y is equal to b plus mx. So y is equal to mx plus b. So this equation would be for simple linear regression. And this is if you only have one feature. And one thing I want to point out, because I see this question sometimes, is why do we use m in our simple linear regression equation, but then we're using beta, or like sometimes people use theta. Like I've seen a lot of different terms used for the model parameters. So the reason why you typically see m in this equation for the simple linear regression is because that's the slope, and it's tradition to use m to represent the slope. Sometimes this is where it can get confusing too. Sometimes people will use m in the multiple linear regression equation. So I'll just specify. So this equation, this is the multiple linear regression equation, and this is if you have multiple features, and then this is the simple linear regression equation, and this is if you just had one input feature or one independent variable. And so in the multiple linear regression, you'll see people use beta, theta, m for the model parameters. Don't get confused by that. Just look at just look at the equation, and from the equation what the different variables are. So don't get too caught up on what symbol people are using to represent the different variables. All right, so what I want to do is rewrite the multiple linear regression equation in a way that I think is a little more helpful to visualize what's actually going into our equation. We don't just have one y or one, this is actually a vector. So we're going to have a vector of y's. And so these are, that should be lowercase, these are our observations. So we might have n observations, and then this is equal to beta naught, and then beta naught is always multiplied by 1, so this is going to be a vector of 1s for n number of 1s, plus, and then we have beta 1, and then x 1 1, so this is our, so if we're looking at housing data, these x's might represent number of rooms, so we have like x number of rooms for our first observation and X number of rooms for our second observation, and so on to n number of observations that we have. Plus, and then I'm going to just say ... plus, and then beta k, so k is representing the number of features that we have. And so then this is going to be x1k ... x nk. All right, so now that we have this in kind of vector form, what we want to do is combine the x terms into a matrix and the beta terms into a vector. So how that's going to look is we still have our observations, so y1 to yn, and then this is equal to, and then if we combine all of our x terms, first of all, we know that the first column is going to be all ones. So 1, 1, and then our second column is x1, 1 down to xn1, and then however many columns of x for how many features we have. So this is x1k, and then that's down to x nk. And then this is going to be multiplied by our beta vector, which is beta naught, beta 1 ... down to beta k. So seeing the equation in this form, I think, makes it a little bit easier to see what we're actually solving for. So we're going to be solving for this beta vector. And so what I want to do is rewrite this in a more compact form. So we can write this as y is equal to x beta. So then if we look at this, it's like, okay, so we're solving for beta, and this equation can have either exactly one solution, it can have infinitely many solutions, or it can have no solution. And the case that we're going to be considering is the case where there's no solution. If there's no solution, that means that we can't solve for an exact solution, but what we can do is solve for an approximate solution. So in order to solve this, we need a way that we can determine if our solution is accurate. And so what we're going to do is define an error term, and what the error term will do is measure how the model's predicted value. So remember, we're going to be calculating some predicted values from the model. And what we're going to do with that predicted value is we're going to determine how it differs from the observed values of y. So our error term can be defined as e, and I have ei because, so this is our ith error value, because remember we have many observed values, so we're going to have many predicted values. So yi minus yi hat, and then we're going to square this. And so the yi, these are the observed values, and then the yi hat are the predicted values. And so basically what we're doing is we're measuring the squared error between the model's prediction and the known value. And what we want to do is we want to pick a model that makes the error between these terms as small as possible, because the smaller the error, the better that means the better our model is. So what we're going to do is sum all of the error terms, and then we're going to make that as small as possible. We can sum these, so s is equal to I is equal to 1 to n, and we're summing all of these error terms, and then this is equal to I is equal to 1 to n yi minus yi hat squared. And I just want to point out this s, this is called the objective function. And so that's basically just terminology from optimization problems, which is what we're doing with this. So then this is equal to y minus x beta squared. So what we want with this is we want the y minus x beta to equal 0, because we want our error term to be 0. If the error term is 0, that means that we have a perfect solution. And so I'm going to rewrite this as y is equal to x beta. In reality, we're never going to have a perfect solution. So the error term is never going to be exactly 0. So we're never going to have y is equal to x beta. It's always going to be y is approximately x beta. And you want to be careful about this too, because you can run a model to try and get like we're trying to minimize the error function, but you want to avoid having a problem of overfitting, which means that your model fits the data that you have really well, but then it only works for that data. Like if you try and make other predictions from it using different data, you're not going to get a very accurate solution. So we want our objective function to be as small as possible, but we also want to make sure that we're not overfitting the model. And so there's a few different ways that we can solve this. The first is that we can use gradient descent. And gradient descent is an iterative solution. The other method that we can use to solve this is we can use an analytical approach. There's actually an analytical solution to this problem, and that the solution that you get is called the normal equation. I'm going to be going over gradient descent and the analytical solution in different videos. If you found this video helpful, please hit the like button or subscribe, and thanks for watching.